Hello, everyone. I'm Ivan. Welcome to the third webinar organized as part of the project From Raw Collection to Digital Collection, co-funded by the European Union. The aim of the project is to enrich the common European data space for cultural heritage using advanced 3D and XR technologies. So before we get started, I'd like to go over a few housekeeping items to ensure everything runs smoothly. Please make sure your microphones are muted during the presentation to avoid background noise. And if you have any questions, feel free to ask them in the chat and we'll address them either during the presentation or at the end, depending on the timing. For any technical issues, please reach out via the chat and we'll do our best to assist you. Also, we would like to remind you that the webinar is being recorded and the recording will be available on our website. Thank you all for being here, and let's start. So today we will cover several topics, including the importance of digitization, 3D scanning technologies and application, as well as extended reality with its components. So let's start by taking a closer look at the importance of 3D digitization. 3D digitization offers key benefits for preserving and accessing cultural artifacts. It helps protect fragile objects such as ancient sculptures or manuscripts by creating digital replicas that can be shared and studied without damaging the originals. Additionally, 3D models enhance accessibility, enabling researchers, educators, and the public to explore artifacts remotely, even from difficult or dangerous locations. These models also assist people with visual impairments, offering tactile experiences through 3D printing. For research and education, 3D digitization allows scholars to study objects virtually, reducing the risk of damage and providing deeper insights. It also aids in reconstructing damaged or incomplete artifacts, offering a better understanding of their original form. While 3D digitization doesn't replace physical preservation, it is a valuable tool for enhancing our ability to safeguard, study, and share cultural heritage. We covered this topic in more detail in our previous webinar, which is available on the RCtoDC website. Also, 3D digitization is very important in advancing the European Green Deal. Launched in 2019 and approved in 2020, a European Green Deal is the EU's strategy to achieve climate neutrality by 2050, aligning with the Paris Agreement's goal of limiting global warming to 1.5 degrees Celsius. It promotes a competitive, fair, and sustainable economy and requires all policy areas, including energy, transport, and agriculture, to support climate action. The EU Council and Parliament have turned this vision into binding laws across member states. So how does digitization of cultural heritage align with the European Green Deal? Well, digitization indirectly contributes to the European Green Deal by reducing physical impact and carbon footprint, promoting virtual access, incorporating green practices into training, actively addressing environmental concerns, and embracing innovative technologies for sustainable cultural heritage preservation. So let's start with a quick overview of the main 3D scanning technologies and how they work. 3D scanning technologies allow us to create digital representations of physical objects. The technology employs various methods and tools, each suited to different kinds of objects and uses. This overview will focus on the different 3D scanning methods, their advantages, limitations, and applications. 3D scanning can be divided into two main categories: contact and non-contact methods. Contact scanning involves physically touching the object using probes to gather data, typically providing high precision, but being slower and potentially damaging for their delicate objects. Non-contact scanning utilizes various technologies to capture the shape and details of an object without direct contact. Non-contact methods are often preferred as they avoid physically touching the object and are generally more versatile for scanning delicate or intricate items. Non-contact scanning methods can be further split into active and passive methods. So non-contact active scanners emit light and measure the reflection of the transmission of this energy as it interacts with the object. Let's take a look at some of the main types of 3D scanning technologies, starting with laser scanners. So first we have time-of-flight scanners, or TOF scanners. These scanners use a laser to emit light pulses and measure the time it takes for the light to return. This helps calculate the distance to various points on the object's surface. These scanners are fast, capable of capturing a large number of data points, and suitable for larger objects like buildings or landscapes. Next, we have triangulation 3D laser scanners. These use a laser beam and a sensor placed at a known angle. When the laser hits the surface of the object, the reflection is captured by the sensor, and based on the angle of the reflection, the system can calculate the position of the point. This method is typically used for high-precision scans of smaller objects. So moving on to structured light scanners. These scanners project a pattern of light onto the object. As the light deforms across the surface, a camera detects these deformations and calculates the distance to the object's surface. These scanners can capture large sections quickly and are very precise. There are two main types of structured light scanners. White light scanners, which use white light patterns and are known for high accuracy and color capture. They're often used in quality control and reverse engineering. Then we have blue light scanners, which work similarly but use blue LED light instead of white light, which tends to produce higher contrast and less interference from ambient light. This makes them ideal for scanning shiny or reflective surfaces. And finally, we have volumetric scanning methods, which are commonly used in medical and industrial applications. So we have computed tomography, or CT, and magnetic resonance imaging, or MRI. These are primarily medical technologies that create 3D representations of the interior of an object, or usually body. So they use X-ray and magnetic fields instead of light. These methods are also used in industrial applications for non-destructive testing and reverse engineering, particularly when examining internal structures of an object. So next we have non-contact passive scanning, which relies on capturing light naturally reflected from the object's surface without emitting any energy themselves. A common example of non-contact passive scanning method is photogrammetry. Photogrammetry involves capturing multiple photographs of an object from different angles and using software to reconstruct the 3D shape. The result can be a 3D point cloud or mesh. This method is highly accessible and often used on cultural heritage, archaeology, and architecture. Applications range from small-scale objects to large-scale environments, such as entire buildings or terrains. Structure for motion, or SFM, is a technique used in photogrammetry which creates 3D models from a series of 2D images. It's widely used in cultural heritage due to its accessibility and ease. Also, there is aerial photogrammetry, which includes capturing images from drones, planes, or satellites to generate 3D models of large structures, landscapes, or urban areas. So these are some of the more popular manufacturers of the equipment used in 3D scanning of cultural heritage. This equipment uses a combination of various 3D technologies to capture, preserve, and analyze cultural sites and artifacts in great detail. 3D scanning technologies have evolved to cater to a diverse range of applications, from industrial design to cultural preservation. Understanding the different methods, whether active or passive, contact or non-contact, helps determine the best approach for each project. With continual advancements in speed, precision, and resolution, 3D scanning will continue to open new possibilities across industries, providing deeper insights into both our present and our history. So let's take a look at some examples of 3D scanning in cultural heritage. One of the more famous examples is the Rosetta Stone. The British Museum employed high-resolution 3D scanning to create a precise 3D model of this iconic object. This approach serves several purposes. It safeguards the original, enables detailed research, and significantly broadens access for audiences worldwide. Such digital models allow for remote interaction, ensuring that students, scholars, and the general public can examine the artifact closely, regardless of their geographic location. Similarly, Egyptian mummies have been digitally preserved using non-invasive techniques such as CT and 3D scanning. This enables researchers to study internal structures and burial practices without disturbing the physical remains, providing new insights into health, society, and rituals of the time. Beyond individual artifacts, 3D scanning plays a vital role in documenting entire archaeological sites. A notable case is Pompeii, where ongoing 3D scanning projects are digitally capturing ruins and recovered objects. These digital records are crucial for in-depth analysis, reconstruction efforts, and for creating virtual experiences that educate and inspire. And another example is the Cave of Altamira in Spain, which is home to some of the world's earliest cave paintings. Due to the fragile nature of the cave environment, access is highly restricted. By scanning the site in 3D, scientists and the public can now experience these prehistoric artworks virtually, preserving them for future generations while minimizing human impact. Many cultural heritage projects stop at this point, using the 3D data for illustration or scientific purposes. However, this data can be treated as a foundation to create XR content and environments that can be used or evaluated by experts. Now my colleague Mirna will tell you more about extended reality.
Hello, everyone. So first, we need to ask ourselves, what is extended reality? Extended reality is a rapidly evolving term that refers to a combination of digital and physical environments, enabling interaction between humans and machines through computer-generated technologies. The XR landscape comprises three main categories: augmented reality, virtual reality, and mixed reality. These technologies are gaining widespread adoption across various industries, from entertainment and education to healthcare, manufacturing, and beyond. Now let's take a closer look at each component of XR and understand their unique characteristics. In the simplest terms, virtual reality is a fully immersive computer-generated simulation of a three-dimensional environment. VR environments aim to convincingly simulate reality, making users feel as though they are inside a world created entirely by computers, in a way just like how people move within or inside a natural environment. While immersed in the virtual world, the real world that surrounds the user cannot be perceived by the user. The goal is to transport the user into a space where real-world surroundings are no longer perceived. In recent years, VR, which was once associated primarily with gaming and entertainment, has now expanded to applications in education, training, and even mental health therapy, where users can interact with virtual environments for a wide range of purposes. On the opposite end of the spectrum from VR, augmented reality overlays virtual elements on top of the real world. Rather than replacing reality, AR enhances it by superimposing computer-generated images or data onto the user's view of the physical environment. AR can be experienced through devices like smartphones, tablets, or smart glasses. It is being widely adopted in industries such as retail, real estate, and healthcare, allowing for the enhancement of products and services with digital overlays and real-time data. It is often used in gaming, navigation, and industrial applications. Mixed reality takes the concept of AR a step further by creating a hybrid space where both physical and virtual objects coexist and interact in real time. MR is often considered a blend of AR and VR, allowing for a seamless combination of real and virtual worlds where both physical and virtual elements can interact dynamically. MR has incredible potential for applications like quality control, design prototyping, and remote assistance. For example, MR-based interfaces are being used to improve ergonomics and productivity in sectors like manufacturing and maintenance. It is ideal for collaborative tasks where real and virtual worlds interact, like in product design, remote collaboration, and hands-on training. So to simplify, VR creates entirely virtual spaces where users are fully immersed, disconnected from the real world. AR supplements the real world with virtual objects, creating a mixed reality that enhances the physical environment. And MR blends both physical and virtual elements in such a way that the user can interact with both in real time. Let's now explore how extended reality is applied in practice. Virtual reality is being used in museums and educational institutions to create interactive three-dimensional environments. For example, the Oculus Quest 2 is popular for creating accessible, cost-effective virtual tours of ancient sites. The HTC Vive, with advanced tracking and resolution, enables more immersive, interactive experiences, such as virtually restoring objects or walking through historical reconstructions. As for augmented reality, common devices such as smartphones and tablets use AR apps to provide enriched exhibition content, offering annotations, historical reconstructions, and interactive storytelling. Advanced devices like the Microsoft HoloLens take AR further by enabling spatial interaction with 3D objects. This is used to inspect artifacts, simulate ancient architecture, or visualize historical layers in real-world settings. Supporting these technologies is a range of software platforms that convert raw data into meaningful digital experiences. Agisoft Metashape and Meshroom are widely used for processing 3D scan data into clean, usable models. Blender, an open source tool, is ideal for detailed modeling and visualization, especially in virtual reconstructions. And it is also often used to further clean up and prepare scanned models for future use in XR. Unity and Unreal Engine are industry-leading platforms for building interactive XR environments. Museums have used them to create fully immersive virtual walkthroughs and educational games based on real historical content. XR technologies are advancing rapidly due to continuous improvements in both hardware and software. As these technologies mature, their influence will continue to grow. The next decade promises even more innovative applications, from interactive learning environments to digital twin simulations and beyond. To summarize, XR is a powerful and transformative field that includes VR, AR, and MR, each contributing in unique ways to our experiences and workflows. So whether you're in education, cultural heritage, healthcare, entertainment, or manufacturing, XR technologies offer immense potential to reshape industries and create new opportunities for innovation and engagement. As we explore the future of XR, the line between the physical and digital worlds continues to blur, opening up new possibilities for how we interact with both. There are many ways in which we can implement these technologies into cultural heritage institutions, and the following examples from across Europe will illustrate how they are already being effectively integrated into practice. The first example is the VR experience from Musée d'Orsay. The Van Gogh's Palette is a 10-minute interactive VR journey, immersing visitors in Van Gogh's artistic process, particularly from his time in Auvers-sur-Oise. Equipped with VR headsets, visitors found themselves in Dr. Gachet's drawing room, where Van Gogh's portrait of Margit Gachet was displayed. A paint-smeared palette on the table served as a portal into an immersive landscape, guided by elements like the Kingfisher painting. Participants engaged with Van Gogh's artistic methods, manipulating colors and brushstrokes, all set to reimagined piano transcriptions of Wagner's operas, reflecting the artist's admiration for the composer. The Mauritshuis Museum introduced an innovative HoloLens experience centered around Rembrandt's painting Saul and David. This augmented reality application allowed visitors to delve deeper into the painting's history and restoration process. By wearing the HoloLens, users could virtually peel back layers of paint, revealing hidden details and the meticulous research that was undertaken to authenticate the artwork. The De Young Museum in San Francisco partnered with Snap Incorporated to bring an interactive fashion experience to life in its Fashioning San Francisco: A Century of Style exhibition. Opened in 2024, visitors could virtually try on 3 iconic evening wear outfits by Yves Saint Laurent, Valentino, and Kai-Sik Wang. This innovative partnership allowed guests to digitally experience high fashion, further bridging the gap between fashion history and modern-day technology. The National Gallery in London utilized augmented reality to bring iconic artworks to life beyond the museum walls. With an AR app, users could see famous paintings by artists like Titian, Van Gogh, Serot, and Amin superimposed onto the streets of London. At the Smithsonian Institution in Washington, D.C., AR technology was used to breathe new life into its bone hall, which has displayed skeletons since 1881. Through the Skin and Bone app, visitors could see virtual skin and muscle reconstruct skeletons and observe how certain animals moved. The app provided a fascinating glimpse into the history of these ancient creatures, helping users visualize what they may have looked like in their prime. This innovative experience aimed to bring untold stories of the museum's collections to the forefront. The National Museum in Prague introduced an innovative AR mobile app to enhance the visitor experience. Using markerless AR technology, visitors could bring to life the museum's iconic fin whale exhibit by simply pointing their phones at the display. This experience allowed the whale to appear in full digital form without the need for visible markers, preserving the museum's aesthetic. The project demonstrated how AR can blend education with entertainment to captivate diverse audiences and provide immersive, accessible cultural experiences. A new visitor center in the Ghent Cathedral uses AR glasses to enhance the visitor experience without impacting the cathedral's aesthetic. The center provides a personalized AR tour starting in the crypt, where visitors are guided by a digital assistant through various chapels. The AR layers bring the cathedral's history to life, including the creation of the famous Ghent altarpiece. After the AR tour, visitors can view the actual painting, which provides an innovative and memorable experience. The Historium takes visitors back to 1435 to explore the Golden Age of Bruges, a UNESCO World Heritage City. Combining immersive storytelling with film, audio, aromas, and special effects, the museum transports visitors to medieval life. A VR experience allows guests to sail through medieval Bruges, seeing the city as it was over 500 years ago. With over 300,000 visitors annually, it's one of Belgium's most popular and innovative museums, appealing to a wide range of audiences through multisensory, family-friendly experiences. The Walk in Bruegel's paintings experience invites visitors to step into the 16th century through VR. Guided by Peter Bruegel himself, visitors explore medieval life, attend celebrations, and witness key moments like the introduction of the New World. The experience features realistic movements in the paintings, bringing Bruegel's art to life with period-specific music. These diverse examples illustrate how extended reality is revolutionizing cultural heritage experiences across the globe. Whether through virtual or augmented reality, museums and institutions are embracing technology to create more immersive, interactive, and accessible ways for audiences to engage with art, history, science, and storytelling. From stepping into the world of Van Gogh to virtually sailing through medieval Bruges, these innovations are not only enhancing visitor engagement, but also redefining how we preserve, interpret, and share cultural narratives in the digital age. And now my colleague Matea will present an example of 3D digitization from our RCtoDC project.
Hello, everyone. So in this section, we'll be taking you through an example from the RCtoDC project, where we combine the power of 3D scanning technology and digital modeling to capture a historical masterpiece. Specifically, we'll be showcasing the 3D digitization of Francesco Roba's altar of Saint Barbara, located in the Church of Saint Martin in Varaždinske Toplice, Croatia. This altar is a renowned Baroque piece by Francesco Roba, a key artist of the 18th century in the region. In the RCtoDC project, we focused on artworks by Francesco Roba in 3 countries: Croatia, Austria, and Slovenia. This altar represents an important piece of cultural heritage, and our goal was to preserve and present it digitally in the most accurate and interactive way possible, using state-of-the-art 3D scanning and modeling technologies. The altar of Saint Barbara is a highly detailed and intricately crafted altar. Capturing such an intricate structure required precision and attention to detail, as every sculptural element needed to be captured faithfully to preserve its historical integrity. The scanning took place in the Church of Saint Martin, located in Varaždinske Toplice. This location added a unique challenge and opportunity, as we had to account for the church's lighting, architectural design, and the surrounding environment, ensuring the digital model reflected the true atmosphere of the space. As for the equipment, we use the Artec Leo, a high-precision handheld 3D scanner for the on-site scanning process. The Artec Leo is an ideal tool for this kind of work, as it allows us to capture highly detailed textures and geometries quickly, while being mobile and flexible enough to work in tight, complex spaces like the church. The Arte Clio was chosen because of its advanced features. It's a handheld scanner with automatic texture mapping and onboard processing. The scanner provides real-time 3D visualization via the built-in touch panel screen, which was critical when scanning in such a detailed and confined space. This allowed us to immediately check the data and make adjustments as needed. The Arte Clio enabled us to capture every detail of the altar, from the fine carvings to the intricate textures. Its high 3D point accuracy of up to 0.1 millimeters ensures that every aspect of the outer surface, no matter how small, is captured. This is important not only for historical preservation, but also for creating a model that could be used in virtual environments and future studies. The working distance of 0.35 to 1.2 meters of the Arte Clio allowed our team to move around the altar, scanning each section without the need for technical expertise. As you can see in the video, the scanning process involved carefully moving around the altar, capturing multiple angles and perspectives to ensure we obtained a complete and accurate representation of the altar. Once the scanning process was completed, we moved to Artex Studio 19 Professional, a 3D scanning software that specializes in creating detailed 3D models from scan data. In the software, we processed the raw scan data and aligned it into a coherent 3D model. The software allowed us to refine the scan data, ensuring the mesh was clean and accurate. It also helped us generate textures that added realism to the final model, making sure that even the smallest details, like the intricate reliefs on the altar, were preserved. The final product is a 3D model of the altar of St. Barbara, with all its fine details, colors, and textures. However, this is not the final version of the model. As you can see, it's still a work in progress. Some parts of the altar are currently missing due to limited access during the initial scanning. The altar is quite large and located in a very tight space, which made capturing it fully quite challenging. We plan to complete the missing sections in future field visits to ensure a more accurate and detailed representation. And once the model is completed, it will be uploaded to Sketchfab, an online platform for viewing and sharing 3D models. Sketchfab allows for full 360-degree rotation, and you can zoom in to see the intricate details of the object, and even experience it in augmented reality using mobile devices or VR and AR glasses. Through this interactive experience, anyone with access to the platform can explore the object as though they were physically standing in front of it. This digital preservation is an innovative way of making historical works of art accessible to a wider audience, regardless of location. Building on this approach, the RCtoDC project will digitize 30 at-risk objects from Southeastern Europe by Francesco Roba and other Baroque sculptors. In addition to creating AR experiences for these 3D scanned objects, the project will also develop training materials and an app to support learning about 3D and XR digitization, further expanding access and educational opportunities in the field. In recent years, 3D digitization has advanced dramatically, transforming the way we capture, process, and utilize geometric data. Originally developed for industrial applications, these technologies have expanded into a broad range of sectors, offering unparalleled precision, efficiency, and analytical flexibility. The choice of 3D digitization techniques today depends on the specific accuracy and performance needs of each application. One of the most exciting frontiers for 3D technologies is their integration with extended reality, including augmented and virtual reality. Digital models are now being used in immersive experiences, from online museums and interactive educational platforms to tools that allow people to explore history in ways never before possible. These applications are redefining how we interact with information, turning learning and preservation into dynamic, participatory experiences. Recent advancements in 3D scanning have significantly boosted both speed and resolution. Cutting-edge systems can now capture dynamic objects in real time, such as facial expressions, at frame rates of up to 120 frames per second. These technologies can record thousands of data points every second, enabling the rapid creation of high-density, detailed 3D models. AI is playing a transformative role in this evolution. AI-assisted 3D scanning streamlines complex processes such as object recognition, noise reduction, and even the reconstruction of damaged or incomplete artifacts. These enhancements not only reduce processing time, but also increase the accuracy and usability of the resulting models. In the near future, AI-based reconstructions could automate the completion of fragmented historical objects, drawing from existing data to recreate missing parts with extraordinary precision. Hardware innovation is also democratizing access. As scanners and headsets become more portable and affordable, smaller institutions and field researchers are gaining the ability to participate in digital preservation. Miniaturized, high-quality scanning equipment can now be deployed in the field, allowing for real-time documentation and conservation work. So looking ahead, the possibilities are vast and inspiring. Real-time, cross-continental collaboration in shared virtual environments will empower archaeologists, historians, and conservators to work together like never before. Integration with smart cities and digital twin technologies will embed historical sites into urban digital ecosystems, enabling simulations, predictive preservation, and interactive public engagement. And thank you so much for joining us for today's webinar. We appreciate your time and interest. Before we wrap up, we would like to invite you all to follow us on our website and social media accounts for more information about the project. And of course, stay tuned to hear about our future webinars. And finally, we'd love to hear your thoughts. So please, if you could take a minute to fill out our feedback form. Your input helps us make future sessions even better. Thanks again for being with us today. We hope you found it informative.